Thank you for the introduction. I want to thank my friends and the organizers for putting this great workshop together. And it's a challenging task to give a talk at this point because we already showed some of the cards yesterday in the problem session. But I will try to say something new as well. Okay. So the main actors are the following operators. Suppose you have functions C1 with complex support in an ambient dimension n with n greater or equal to 2. Okay? Then you can embed one-dimensional or d-dimensional subspace averages or singular integrals in Rn as follows. In this talk, I'm only going to talk about line averages, but you can think of subspace averages as well. So I parameterize the directions on Sn-1 for now. And I'm also going to truncate. I'm going to define the average along vector v at scale epsilon of the function f to be exactly what I said. Okay. Now I could replace the averaging kernel with a singular kernel and also truncate it at scale epsilon. X plus TV, KT, dt. I don't know how many times this is going to happen. Hopefully, this is the last. With K singular. And when I write H, the epsilon, the kernel is principal value 1 over T. Okay, so I have averaging operators and I have singular integral operators. I'm going to define maximal versions or vector field versions of these and maybe say something about two of them. One nice problem is the following. Let V be a vector field Rn to Sn-1. There's no damage in. And let's say that vector field is Lipschitz. You can cook up the following maximal operator that depends on the vector field V. Okay. Supremum over all epsilon greater than 0 of AV of X epsilon F. Okay. This is called sometimes Zygmund maximal operator. And the fact that you have the vector field is Lipschitz becomes useful if you restrict your scales to be much smaller than 1 over the Lipschitz constant. Okay. This restriction prevents usual Kakeya type counterexamples because you can construct a vector field. Otherwise, you can construct a vector field that points along a Kakeya set. And if you don't, which is also Lipschitz, and the counterexample becomes effective if you allow scales that are greater than 1 over the Lipschitz constant. Okay. There is a nice companion operator, which is the vector field version of the Hilbert transform version. It's simply H along V of X. And the scale you truncate is 1 over V lip. Okay. And this is sometimes called weak L2 boundedness for these are respectively referred to as the Stein conjecture and the Zygmund conjecture. Okay. Why? I mean, it is obvious why this operator one would care about, right? It gives you its L2 boundedness, weak L2 boundedness, gives you differentiation type results. This is a bit less obvious, so maybe let's try to motivate it a little bit. Let's go to the untruncated. Case. In that case, HV is simply the directional Hilbert transform. So I can write it in frequency as f hat of psi times a multiplier, which is the half space restriction. And the half space is taken in the direction perpendicular to V. This is your multiplier operator, okay? And if you have a vector field, or if you have a finite set along which V varies, you can construct the vector field version or the maximal version. Okay. So why is this operator nice? Where are the difficulties coming from? The difficulties are coming from its close connection to the Carlson operator. Let me show you why. Okay. So let P1 be a little P projection to the second frequency variable, roughly 1. Okay, so I'm gonna place a smooth vertical in the sense that it's in vertical variable cutoff. Okay. Well then, if f hat is supported on a line in psi to roughly 1, HBF is essentially a Carlson operator. Okay. Why? Because if this is where your F is supported, rotating V means rotating the subspace. And so it means you're going to change, you're going to truncate F hat to frequencies less than n of x, where n of x is the intersection of V of x with the support of f. Okay. Of course, this is formal. You can make this precise. And one more connection is understood when looking at how to analyze these operators. Okay. Let me redraw the frequency multiplier of the Hilbert transform in the direction V. And let me this time do an annular little Perry decomposition. Okay. So let's say this is the direction V perp, is the subspace orthogonal to V. Okay. I can do a multi-resolution decomposition of the annulus using tiles of a given scale, angular scale, and I'm going to use color to do that. It means I do an angular decomposition, and so I get tiles. This is one tile. This is another tile. And I've done this for a certain angular scale. I can do it for a smaller scale as well. And I'm going to use a different color. So this is a smaller scale tile. And this is another small scale tile. So you can then discretize HVF much like the Cartesian operator. So this is going to be the sum over all tiles. Think of this as the frequency component of a tile. Its spatial rectangle dual is something that has reversed the relations and points in the direction perpendicular to it. So something like this. Okay, so you do a Gabor decomposition. But then you keep only those tiles whose they have the property 2 omega minus omega contains V of x, right? Because if you have to discretize this singularity, you are going to do a little Pellet decomposition in the angular variable of this singularity. And so you're going to get that if you double the uncertainty interval, you're going to hit the perpendicular plane. And if you are familiar with Cartesian operators model sum, this is exactly analogous. The difference is that, first of all, you have product. I mean, the single tree is a product Hilbert transform. It's no longer a Hilbert transform. Okay? Why? Because you can view this multiplier as a singular or degenerate, let's say, not singular, degenerate two-parameter multiplier. Hilbert tensor in one variable, tensor the identity in the other variable. Okay? And of course, these tiles are biparameter, and when you take all the possible directions into account, they also have directional nature. Okay? So the first question I'm not going to talk about is the following. Replace V of x by a finitary object. Okay. In either problem, for the maximal operator or for the vector field Hilbert transform. So let V be a subset of Sn minus 1, and consider the maximal operators. HV F equal the supremum over all V in your finite set V of the Hilbert transform along V. And the same for the maximal operator. These are the objects I'm going to talk about for the remainder of, and here I have also the supremum over scales of the average along V at scale F. Okay. Given that V is finitary, we in general do not have any type of smoothness conditions, such as the Lipschitz assumption. So typical questions are of the form, find the sharp dependence of MV operator norm, I don't know, for instance, from 2 to 2 infinity, on the cardinality of the set. The question for the maximal, so the question for the maximal operator in 2 dimensions, this has the richest history. But the landmark result is due to Netzkatz in roughly 25 years ago. He showed the sharp estimate of weak type 2,2 is controlled by square root of logarithm of the cardinality of V. Okay. So this in particular implies the weaker estimate, but very useful, on the L2 norm, which is 1 more square root of log. Okay. Other contributors here include Cordoba, Stromberg, Scholin and Sjogren, Alfonseca, Soria Vargas, and later Bateman. Okay, so this is it's more or less a geometric proof that uses a TT star argument and a Carleson packing, some sort of John Nirenberg argument. Okay, these arguments are not available for the, or not immediately available for the singular integral version, which is still open. Is it true that the Hilbert transform along n directions has the weak type norm square root log of the cardinality? First of all, this estimate for HV is trivial and well known and trivial because of Rademacher-Menshov. Okay, you can write this supremum as a supremum of partial sums of disjoint frequency regions, and so Rademacher-Menshov applies. I'm not going to do that. If you replace the Hilbert transform by a different kernel, the result is still true, but not at all easy to prove. Okay. So in fact, so Demeter using lazy Lie technology shows that for a different kernel, analogously defined operator, the bound is logarithmic in the number of directions. Okay. In a paper joint with Demeter, I show that this estimate, we show that this estimate persists up to higher order logarithms that I willfully ignore here for 2 categories of sets, V Lacunary, and also, which is sharp due to a counterexample by Garagulian, and also the vanilla set of cardinality n, e to the 2 pi I j over n, j from 0 to n minus 1. Delta net, 1 over n net. Okay, so this problem, these partial results require the understanding of a Carleson type model sum with product tiles, which is rather unusual because product theory does not mingle well with a few of the quantities specific to Carleson operator, such as the density. Okay, there is no order relation on tiles, and this makes it more challenging, more interesting. To overcome these difficulties, you exploit heavily the structure of directions. But I'm wondering if there are clever ways to avoid exploiting explicit properties, rather than using them. Analytically, it is pretty clear that you have to work using Carleson type model sums, or at least the difference between this estimate and the L2 estimate is rather striking in that sense. Okay, so if you're interested, please join group 5, and we are working on a different problem, but we should absolutely talk about this one as well. Okay, another finite array problem, which is not completely solved, is what happens when for the maximum function in dimensions 3 or higher. Okay, and I will begin with a small principle. This is valid in all dimensions. So this principle is called the switch lemma. Okay. I have drawn many times the symbol of the directional Hilbert transform. I haven't drawn the symbol of the averaging operator, so let me do that. Take a vector v, okay, and let me draw the average along v at scale 1 over s. Okay, in frequency, this is a slight feathering at scale. This goes on forever. At scale roughly s of the hyperplane perpendicular to v. Okay. So this is essentially the same as taking f and multiplying it by some smooth function of psi dot v over s. Okay, nice. Now, the switch lemma tells me that if I have a different direction, let's say w, and the angle between them is delta, then AVS, AV1 over s, composed with a little Wood-Paley projection at scale s over delta, is basically controlled by the maximal function along w. Okay, and why is it the case? Because basically at scale between 0 and s over delta, these two tubes can be switched one into each other, and so you look at the symbol and draw the conclusion. Okay, so what remains is, once you have made this observation, you can switch the direction v to w. Okay, what remains is going to be supported in a cone. Okay, and this cone is the cone I'm going to draw now. So this is the cone psi dot v less than delta. Okay. Identity minus p s over delta supported in this cone b v delta. So these are the psi in our n, such that psi minus 1 psi times v is less than delta. And you can put norm of v when we will have slightly more general v. Okay. Good. So this switch lemma is very useful because it really creates a lot of principles that go under the moniker of almost orthogonality. Okay. One is the following. I want to stick to my notation here. Okay, so let V be a subset of the n-1 dimensional sphere. P be a polynomial of degree d. and ZP be the zero set of the polynomial on the sphere. Okay, so let's make a small drawing. This is your two sphere. There's a zero set of a polynomial, and then you have omega, the connected components of S n-1 ZP. This should remind you of something. That's the setup. And finally, I'm going to erase. So what you want is the following estimate. Then there exists a subset VP of the zero set of P on the sphere of cardinality, at most the cardinality of V, such that the maximal operator norm of the set V is controlled by two components. One is the maximal operator of the set VP, which leaves, the set VP lives on the zero set. V lies around the sphere. We don't know where it is. Plus another constant times d to the power n-1 over 2 times the supremum over all connected components of the complement of the zero set of MV intersection that connected component. Okay? Now, in real life, why would you ever think of this problem? Okay? Because this reduces the estimate for the maximal operator associated to a general set to an inductive term where you, if you have chosen the polynomial correctly using polynomial partitioning, the number of directions in each cell is substantially decreased. Okay? And the current term is a term of directions that live on a lower dimensional algebraic variety. Okay? This guy, ZP, has dimension n-2, because it's one more equation. Let's be, let's not be precise. Okay. So this principle alone would be a good reason to consider the following problem. My goal is then to have the best possible estimate on algebraic subsets of dimension. So the general problem is the following. Given a semi-algebraic subset of Sn-1 of degree D, show the following estimate, that the constant Q, Zn, defined as the supremum over all subset V of Z of cardinality less than or equal n to the, so Z is semi-algebraic of degree D and dimension, so let's do n to the dimension of Z. Okay, maybe let's call dimension of Z equals m of the operator norm of MV. Okay, so you can conjecture that for every epsilon, this is going to be less than or equal than n to the power m minus 1 over 2 plus epsilon. Okay. And let me say something about the story of this problem. The remark, the single scale case, single average, is solved by us. After that, this paper appeared, Kim and Harmonic did it for HV. Same quantitative bound. Now, the symmetry of the multiplier of the Hilbert transform is very important. And one can even guess this by looking at what happened for the case m equals 1. The case m equals 1, HV is in a paper of Christ, Duan di Cochea, and Rubio de France. And the single scale is actually due to Cordoba in a beautiful paper from '83. The paper is called for Geometric Fourier Analysis. Okay, I still have 12 minutes, right? We started 10 minutes. Good. So notice that this problem is non-trivial even when m is equal to n minus 1. Okay. The only case, so the full dimension case where there is no, the same algebraic set is essentially the whole sphere. So this is completely settled only in dimensions n equals 2. And in fact, the one that I wrote is a much weaker version of Katz's bound because it's n to the epsilon in that case. Okay. So in some work, we show the case m equals 1, arbitrary n. Okay. And there is also a corollary of the m equals 1 case, which is the following. The n equals 3, m equals 2 case is a corollary. How do you get this corollary? Well, you have that this guy will contribute n to the epsilon when you partition appropriately a generic set of n squared directions. Okay, then you apply polynomial partitioning many times and use the almost orthogonality principle. Okay. So the proof uses yet one more almost orthogonality principle. For curves that we call basic. If I have time, I will tell you what basic curves are. Basic curves are curves that can be decomposed into pieces of controlled curvature. So of course, if a curve has curvature bounded from above and below, this curve will be basic. Otherwise, you enforce a small turning condition, doubling condition on the integral of curvature, and oscillation condition on the curvature. Okay. And then the more sophisticated technically part, but maybe less interesting, is decompose a semi-algebraic set into basic pieces. Okay. Okay, I don't have time to show you the whole plethora of details of the proof, so I will focus for like 10 minutes, 5 minutes, whatever, on the case Z equals a circle on on S2. And I will just explain you where the geometry of curvature is actually entering. The algebraic portion is this one. Okay. So the observation is related to those cones that I have erased, to the cones we used when we talked about the switch lemma. Okay. Maybe erase this. So let's remember what these cones are. So if you have that Z is a circle on S2, we can write it more or less slightly changing coordinates the following way. It's a curve V of S, arcane parameterized of components 1, cosine of S, and sine of S. Okay, with S in a small interval. Okay. So now for each delta greater than 0, define the cone B S delta to be the set of those psi in S2 such that psi dot V of S is less than delta. Okay. The observation is that, so let S1, S2, S3 be 3 parameters. And delta J, for each J from 1 to 3, be a thickness chosen much smaller than Si minus Sj for all pairs. Okay? Then, if you do that, the triple intersection B S1 delta 1 B S2 delta 2 intersection B S3 delta 3 is empty. Okay? And this is a quantitative version of the fact that only given 3 different points, the tangents to a circle, on a circle, the tangents to a circle will intersect in 3 different points. I'm done. How? But I started at, don't I have 40 minutes? It's 11:09. Well. We started 1 minute late. That's, this is a quantitative version of the fact that the intersection between tangents to 3 different points at 3 different points in the circle is never going to be the same. And in fact, there is a separation condition. The curvature is what is creating this separation condition. Okay, that's all. Thank you. I will not write anything because it's probably easier if I speak. The easiest so the answer is no. The obstruction is not algebraic, and it's not even differential geometric. It's analytic, because we haven't figured out what the right quantity is, as opposed to curvature in the one-dimensional case, that create orthogonality are.